So as we stated earlier, an electromagnetic wave really is a traveling quantity of energy that propagates through space. And what this means is that a wave moves or carries energy from one point in space to another point in space. And how it does this, how an electromagnetic wave is able to achieve this, is by establishing an electric field and a magnetic field in space as it moves. As such, an electromagnetic wave that composes electromagnetic radiation is a self-propagating transverse oscillating wave. By self-propagating, we mean that by establishing an electric and a magnetic field, it continues to propagate throughout space. And in fact, if the medium is lossless like a vacuum, an electromagnetic wave will continue to propagate throughout space for infinity. It'll just keep going and going and going. By transverse, we just mean that it has two components. And these two components are orthogonal to one another, or they're at 90 degrees to one another. And the last is that it's oscillatory or periodic. We just mean that it follows a sine wave or cosine wave function, as we've shown here. So in the diagram on the top here, I've drawn an EM wave, and I've drawn it as propagating in the positive x direction, meaning that the wave has a propagation velocity that's taking it from the left to the right across the screen. The electric field established by this EM wave is in the vertical plane, and I've drawn it in blue here. And the magnetic field that is established is in the horizontal plane or coming out of the page, and I've drawn it in red. Commonly, the electric field is called the E field and given the symbol capital E, and the magnetic field is called the B field and given the symbol capital B. Sometimes this will be called the H field and given the symbol capital H. We'll discuss the reasons for this later. What I want to point out now is that you'll notice there's a little arrow drawn over some of those, and sometimes or both of those, and you'll see sometimes it's drawn as E hat or B hat. People will call that E dagger or E hat. It's got a variety of different nomenclatures depending on whether you're an electrical engineer or a physicist. But what E hat are and B hat, or what E and B hat are vector quantities. That means they've got a magnitude and an angle. Not only is there the size of this electric field, the amplitude or the peak amplitude of this electric field, but it points purely in the z-axis. Not only is there the magnitude of the magnetic field, but it points purely in the y-axis, meaning it doesn't point in the z-axis. It doesn't point in the x-axis. Its magnitude points out into the z-axis. And so these are vector quantities. And so, you've written vector quantities before. You may read it as E peak at some sort of angle. That's one way that we've written it in the past. We'll see in electromagnetism a lot of times what we'll write as an E peak, and then we'll multiply it by what's called the unit vector, such as the unit vector in the z direction for the electric field here. And this nomenclature just means that electric field vector points purely in the z direction. You don't have to remember that all now. You just have to remember that E and B are vector quantities. So what I want you to recall next is that current is actually the flow of charged particles. Typically, we consider it the flow of electrons, which are negatively charged particles. Each of these electrons, if I've just got an electron sitting there, some sort of electron just sitting there, it's going to have an electric field associated with it. If it's just sitting there and I were to put a positive test charge in there, that positive test charge is going to get pulled directly towards the electron. It's not going to curve, it's not going to do anything. If it's just sitting there, it's going to get pulled straight in, just like two magnets would. So it's got an associated electric field that is radiating towards it in all directions. If this electron were for some reason to get, I'll just change colors here, if it were to get accelerated, from left to right, what's going to happen is it's going to produce a magnetic field that's going to surround it in concentric circles. So you're going to get this electron that's moving, and it's going to establish this magnetic field around it as it moves. And so it's still also going to have this electric field as it moves. So a stationary electron has an electric field. A moving electron has a magnetic field and an electric field. And current is moving electrons, right? So in this picture right here, I've got a printed circuit board. This middle section right here represents a trace that contains some sort of signal. Maybe that's a digital or analog signal. And then we've got a ground plane right here. So what is going to happen then is, because there is electric charge on this plate, we're going to get an E field shown in blue that points from the positive, or from the positive charge to the negative charge, or from the trace to the ground plane. And so we see that this electric field radiates out into space and into adjacent traces and planes. Because the charges are moving in that conductor, magnetic fields are going to circulate around the trace. So the pattern of both these fields is going to depend on the relative direction and the magnitude of the currents that are flowing in all of the different traces, and also on the material properties of the board and the surrounding environment. And this is really why we are concerned with electromagnetics as electrical engineers. It's how do these magnetic fields and electric fields influence the space around them, meaning how do they influence the circuit traces, how do they influence the material that circuit traces are on, and then how do they influence neighboring circuits. And so that's really how the electric fields affect these circuit boards or circuits that we're interested in.